Completely switching gears now. I've been hinting throughout the semester that we will eventually talk about how a database engine stores information and what kinds of data structures it uses in order to be able to efficiently execute queries. And I actually talked a little bit about this on the very first day of class. So I showed this slide where I have a few student records where everyone has certain fields like name and major and so on. And you have to imagine that there are millions of these records. And so each one of these records would be like a row in a table, in the students table. And depending on what I'm doing, I would want to be able to ask different kinds of questions about this data. So sometimes it might be useful to look up a particular student by name. So how do I search through millions of records to find one with a particular name? Sometimes I might want to find all students with a certain major, or sometimes maybe all students with a GPA lower than some threshold or something. So I could maybe sort all of these rows by name every time I want to look someone up by name, and then I would have to resort them by major every time I wanted to look someone up by major, and that's obviously impractical. So what we saw even on the first day of class is we build auxiliary data structures that point to the actual records. So something like a search tree, where I can build one search tree where the nodes just contain names and is thus ordered by names, and then the nodes contain a pointer to the full record. I could build another search tree where the nodes contain GPA values and they point to, and the nodes point to other full records. The structures of these two trees are different because they are ordered on different criteria, and they each point to the full record containing the appropriate information. So these trees themselves are not what holds the raw information. They just hold information about how to find the full information. And turns out these auxiliary data structures here are called an index. And I've hinted at that a little bit throughout the semester. And the term index, though, is not like the term, like an array index. It's more like the index at the back of a book. It's information to help us find other information. And let me just clarify a little bit before going any further. This is just a rough idea. We'll see exactly how these data structures work. Some of you might be wondering, though, like how would we handle duplicates? Obviously, lots of people are going to have the same GPA. And the real data structure that we'll use will easily be able to handle duplicates. This is kind of just the very basic idea. And we'll look at the details of how these data structures work in the next lecture, but before getting bogged down in those details, let's just see how we can apply indexes to a database and where we might want to use them based on what kinds of queries we're doing. So we're going to look at some simple examples where we're going to try to estimate the cost of various queries, and we'll use this simple example database, kind of like an alternative LMS where I have classes and departments. And in this case, the department in the classes table is going to be a foreign key into the departments table. So first, let's look at a query that just uses the classes table. So select department and name from classes where the class number is greater than or equal to 3,000. This is the table that it would return, but how would we do that? Well, let's look at the classes table. The order of this table appears to be ordered by department. It is not ordered by class number. So the best we could do is a linear scan of every row in that table and look at the class number. So how many rows are accessed in order to process this query? It would have to be all of them. We can't stop early because we don't know that there might be another row somewhere down the line since they're not ordered based on the class number. Okay, what if it is ordered based on the class number? Well, then we could do, something like a binary search, or maybe even more specifically, if we knew that 3,000 level classes were the last classes in this table, then we could just start at the end and work backwards until we see a 2,000 level class. Then we know we can stop and don't need to go any further. But either way, it's going to be something like 3 rows accessed. So it doesn't look like a big deal, but that's 75% as many rows as were accessed when it wasn't ordered. So that's pretty good. And you have to remember that in reality, there are going to be millions of rows here. So, you know, cutting out 25% of them is a pretty big deal. Okay, so what if we have a different query now? Select name from classes where department equals CS. And since I reordered this table based on number to help with that other query, now it is not ordered based on department. So the best we can do is a linear scan. We have to find all departments with CS. It's not ordered based on the CS department, so we have to look at all of them. So 4 rows to process this query. Okay, let's bring the other table back in so we can do a join. So if I want to select building from departments, and that's just shorthand for natural join, so we'll just join where the departments match. Natural join classes where name equals stats. So here is the table that this query would produce. I want to know the building that the stats class takes place in. But how is this table generated? Is it going to do the natural join first and then do the where? In that case, we would have to look at every row, so that would be 7 total, 4 from classes and 4 from departments. But no, the system is smarter than that. It's going to do the filter first, where it will find the stats class. So we can eliminate those other 3 rows. And then it's going to go and use that foreign key to try to find something in the departments table. Assume that this classes table is not ordered by class name, which it's not. So the best way to find this stats class is we just have to do a linear scan. So it's 4 rows to do this filter first. But then the departments table is ordered by department. And that's the thing that we need to look up something by. Once we've found the math department for the stats class, we now need to just find some row where the department is math. So we could do a binary search or something. So that's going to be, you know, maybe 1 or 2 rows depending on how the binary search works. So good. That was, you know, it's fewer than if this departments table was not ordered. And we could do even better if, when doing this initial filter in the classes table, if that table was ordered by class name, then we wouldn't have to search 4 rows to do the initial filter. The point I want to make here, where I'm going with all this, is that if we know something about the order of the table, order of the rows, then we can process the query much more efficiently. So records are physically stored on the disk in some order, which will be good for some queries and bad for others. The records are going to span many, many rows, so n, you know, is the problem size. And if we do a search by an unordered column, then it's a linear time operation. On average, we're going to have to search n over 2 rows to find one specific value. So what can we do? Well, what if we store multiple copies of the data of each table, where each table is sorted on a different column? So we just copy the data and just reorder it. Obviously not. We're already dealing with massive quantities of data. We're not going to store multiple copies of them just to make the queries more efficient. We could sort the records on the desired criteria before each search. And again, that's clearly just not feasible. It would work great if you're only doing one kind of search, searching on one column. But it works horribly if you have to search on anything else. Then you'd have to resort the table every time you do a different query. And searching on different columns is fairly common, so not feasible to do this. So this is where an index data structure can help us. You can kind of think of it like making an extra copy of the database, where each copy is ordered by a different criteria. So here's my copy ordered by class number, and here's my copy ordered by class name, except they aren't full copies. It's just the column that I care about, plus a pointer into the full table for the full row. So I still only have one full copy of the data. Plus, I have these auxiliary structures which allow me to quickly find something in the full table. So the way it works is if I want to find the class with number 2060, would first do a lookup in this table, searching for 2060. And since it's sorted, I can quickly find that row by doing a binary search or something, and then just follow a pointer to find this row. And now I've found the class with number 2060. So instead of a full linear scan of every record, it's a logarithmic search of one smaller table. So for now, we are going to think of these indexes as an actual table. It is useful to think of them that way, where it's ordered by the indexed column, and then it has paired with it, it just has a pointer into the full table. We'll keep them simple for now. We'll see the details of this data structure in the next lecture, and like we kind of already saw, it's going to be a tree of some sort. But for now, you might be worried that this is still going to take up a lot of disk space. So let me go back and let's look at this. This looks like almost double the space of just storing one copy of the table. But in reality, these index structures are much more compact than you might think. And we don't actually even need to store every row for the index. But again, we'll see those details and how that's possible in the next lecture. So let's go back to this example where we were evaluating the cost of a query on these tables involving a join, and let's see what the cost might be with indexes. Before, we were just kind of relying on getting lucky and the tables were sorted in the right order, or maybe intentionally sorting them in the right order. Now let's see what we can do with indexes. So the question is, what columns do we need indexes on? Well, let's look at the query. We're going to start with this filter. So we're first going to look for the class that has the name stats. Okay, so we're going to want an index on that column so we can quickly find that class. But then how do we do the natural join? If we filter first, we're going to get down to just one row. So the natural join is going to compare departments. So here's a foreign key from that row. What it's going to do is take that foreign key and look for it in the departments table. So if we're looking for a department, then we're also going to want an index on that column. So that's all we do, is we create these extra indexes. We have the tables themselves, and then we have these auxiliary tables, data structures that let us quickly search through those tables. So we start with stats. We first query this table. We can quickly find stats in logarithmic time, which will quickly get us to this row. Now we just pick out the column that we're natural joining on, so we've got math, and we plug that into this table, the other index. We can then do a logarithmic binary search to quickly find this row and get over to the department that we're interested in. And then we just select building. So all we do is take out that column out of the row we wanted. So without indexes, we can't assume anything about the order of these tables if we don't know what the primary key is anyway. Without indexes, it's on the order of number of classes plus number of departments. With indexes, it's on the order of log number of classes plus log number of departments. Way faster, especially with more realistic numbers where we would have millions of rows in these tables.